Okay, some solved problems for chapter 43, and here we're looking at boron 11.5, and what we kind of know is this number is going to be equal to A, it's the mass number. This number is going to be equal to Z, that is the number of protons, and since we know that A is going to be equal to Z plus N, we could very easily convince ourselves that N has got to be equal to 6. So it's going to have a mass number of 11, 5 protons, and 6 neutrons. We're looking for the binding energy. The binding energy is related to the mass deficit by E is equal to delta mc squared. And so what we first have to do is we have to calculate the mass deficit. And again, it's going to be the number of protons multiplied by the mass of a proton, plus the number of neutrons multiplied by the mass of a neutron, minus the atomic mass, which we're going to look up in this table right here. So we know that there's going to be equal to 5, and it's going to be 5 times the mass of a proton, and keep all the decimal places here, so 1.0072765 multiplied by U. Then we're going to have our 6 neutrons, and the mass of a neutron is slightly larger, so 1.00866649. We could technically even add the electrons, but it's not very much. And we go ahead and we look up in the table boron 11.5, and that's going to be 11.009305 multiplied by U. Forgot my U right over here. And so my delta M is going to work itself out to be 0.0790669 multiplied by U. Then we're going to say, okay, binding energy, E sub B is going to be equal to delta M multiplied by C squared, where we know C squared is 931.5 mega electron volts per U, so 0.0790669 multiplied by 931.5. So this is going to again be mega electron volts per U, and we're going to work our way out to about 73.65 mega electron volts. Now let's get a little bit of practice doing some radioactive decays. We'll be taking a look at the alpha decay of plutonium, the beta minus decay of sodium, and the beta plus decay of oxygen. And I'll refer to my handy dandy little chart because I put so much effort into making it. Now that I'm actually going to use the chart, I do want to talk a little bit more about this particle that is emitted. An alpha particle is just going to be a helium nucleus. A beta plus particle is sometimes written as this. It's going to be an electron with no mass and a positive charge. And a beta minus particle is just going to be an electron, so it's again going to have no mass and it's going to have a -1 charge. So you will see both notations. And I've gone ahead and I've kind of shorthanded this guy with my alpha, beta minus, and beta plus decays. And I did include my antineutrino and neutrino just to be 100% correct. We're looking for the nuclide, or we're looking for the daughter nucleus, and so we're talking about first alpha decay. And we know that the mass number is going to drop by 4. The atomic number is going to drop by 2. So here we have our alpha particle, which again we could even write as a helium-4 2 nucleus. Plus we're going to go ahead and say, okay, well, 235. That's going to drop by 2, and so this is going to be 92. You go ahead and you take a look at the periodic table of elements and realize that this is going to be uranium, dictated again by the number of protons. Now for this beta minus decay, let's go ahead and realize that, okay, beta minus, no change in mass number, atomic number is going to go up by 1, and so that is going to change the number of protons, it's going to increase it by 1. So what we're kind of left with, no change in mass number, still going to be 24. This is going to be 12. You go ahead and you check that out, it's going to be magnesium. And yes, I am using a periodic table, I don't just know these off the top of my head. Last but not least, we're going to take a look at the beta plus decay. It's going to drop the atomic number by 1 and leave the mass number alone, so that the mass number is going to stay by 15. It's going to drop that by 7, so we've lost a proton, and we have nitrogen. And now a solve problems with half-lives. We have 6 grams of some isotope, and we know its mass number. We know A. It decays at a rate of 0.35 curies, so that tells us dN dt is going to be equal to 0.35 curies. And of course we do want to convert this guy into becquerel, or decays per second, that is the SI unit. So that's going to work its way out to be 1.295 times 10 to the 10th decays per second, using this guy right over here. We're looking for the half-life, and so T1/2 is equal to what? Well, we only have one way to kind of get that. We're going to take the natural log of 2 and divide it by its decay constant, lambda. So we just need to figure out what lambda is. So lambda is going to be related to the decay rate, dn dt. Technically this is an absolute value sign, divided by n. Well, we know dn dt. All we need to do is figure out n. So what we can do is we can figure out the mass of a nuclei, knowing there's 124. So we're going to have 124 multiplied by u, where u is equal to 1.66. And we could say that this thing is going to have a weight, or 1.66 multiplied by 10 to the negative 27th, so 124 multiplied by 1.66 times 10 to the negative 27th kilograms. And this thing would have a mass of 2.0597 times 10 to the negative 25th kilograms. And so the number of nuclei, or the number of nucleides, is going to be equal to 6.13 times 10 to negative 3 kilograms. That's the 6.13 grams. And we're going to divide this guy by 2.0597 times 10 to negative 25. It's actually kilogram per nucleus. So kilogram per nucleus. And we're going to figure out that this is going to have a value of 2.976 times 10 to the 22 nuclei. And so we can kind of come back up here and say 1.295 times 10 to the 10th decays per second, divided by 2.976 times 10 to the 22nd. It's going to give us a decay constant of 4.23 times 10 to negative 13th. And this is going to have a unit of inverse seconds, because this was in decays per second. Now we all need to do is come up here, that is, should be the natural log of 2, and divide that guy by my decay constant of 1.638 times 10 to the 12th. You're going to have a unit of seconds, because I had a unit of inverse seconds. Let's go ahead and convert this guy, because that's a pretty nasty, ugly number. We know that there's going to be 3,600 seconds in 1 hour. We know that there's going to be 24 hours in 1 day, and 365 days in 1 year. And this is going to work itself out to be about 5.1959 times 10 to the 4th year. Okay, now let's take a look at 4339. We have a nuclear reaction, and first we kind of notice that they don't tell us what one of the daughter nucleides are, so we need to figure out what that is. We need to balance the nucleon number, and so what we're going to do is say, hey, look at this, here we have 2 and 14 and 10 left over, so this has to be equal to 2 plus 14 minus 10. That's going to work itself out to be equal to 6. That still doesn't tell us what it is, but we can do the same thing for the protons. We can say we're going to have 1 plus 7 minus 5, and that tells us that this number has got to be equal to 3. So we go ahead and we look that guy up, and we realize that this has to be lithium with the isotope 6 and 3. Now we're interested in the reaction energy, so we need to figure out the masses, and we can just look those guys up in the table right over here. So take a look at this side right over there. This thing is going to have a mass that's equal to the mass of the hydrogen plus the mass of the nitrogen. So again, always keep all the numbers here, 2.01410 and I just pull that out of the table that I talked to. And then we have the nitrogen, 14.003074 multiplied by U. Now let's go ahead and talk about this side, now that we've determined that this is lithium. So this thing is going to have a mass that's going to be equal to, first, the mass of the lithium, look that guy up, 6.015121 multiplied by U. And then we're going to say look this guy up, and it's going to be 10.012937 multiplied by U. And then we're going to say, okay, well, the reaction energy is just going to be equal to the change in mass multiplied by c squared. So we're going to realize that this thing is actually gained a little bit of mass. Let's go ahead and calculate these guys out. This is going to be 16.017176 U, and this is going to be equal to 16.028058 U. And so what this means is it's going to have lost a little bit of mass. So this is going to be equal to 16.017176 U minus 16.028058 U. Multiply this guy by c squared, which is going to be 931.5 mega electron volts divided by U. And realize, okay, this is negative. It's one of those endothermic reactions. So Q is going to be equal to negative 10.14 mega electron volts.